Hello everyone, this is chapter 11.6 where we'll be discussing absolute convergence and the ratio and root tests. So the first thing we need to talk about, of course, is what it means for a series to be absolutely convergent. And here I say a series over the sequence a sub n is absolutely convergent if the series over the absolute value of those terms is convergent. So basically we ignore all sign changes. Just take the absolute value of the term, so you only have a positive series, positive terms in your sequence basically. So series over positive terms only now. And if that converges, then the series is known as absolutely convergent. A series that is conditionally convergent is convergent but not absolutely convergent. And we'll take a look at an example of that in a second. So basically it converges, but it does not converge absolutely. So when you take the absolute value of the terms, it's not the case that it converges actually. Okay, there's actually a pretty important theorem that follows, and it's actually quite easy to prove. The book has a really nice proof. It's pretty short and easy to follow. It's essentially by comparison test. I'm not going to show the proof, but let me just read off the theorem. It says, if we have a series that is absolutely convergent, then this implies that it is also convergent. So absolute convergence is kind of like a stronger case of convergence. In fact, I wrote here, absolute convergence implies convergence. So it's kind of nice to know that if we're absolutely convergent, then automatically we're convergent as well. It's like way stronger of a requirement basically to meet. So here we have the alternating harmonic series that we saw before. We actually saw from 11.5 actually that this actually converges. So this converges, but does it converge absolutely? Well, if it converged absolutely, then that means the series from n equals 1 to infinity of the absolute value of the inside terms, which, by the way, is just the harmonic series. And I know this because the denominator is still going to be n, because it just ranges from integers from 1 to infinity, so the absolute value of those are still themselves. But the numerator is either positive 1 or negative 1. Taking the absolute value of the numerator is just going to give you positive 1. This diverges. So we have a series that converges, but not absolutely, meaning that this converges conditionally. So the result of this example really is that the alternating harmonic series is our first example, and it's probably the best example to be quite honest, is an example of a series that converges conditionally. It's conditionally convergent. So that's all I'm going to say there. Okay. And now we're actually going to take a look at an example using this theorem. We need to talk about it a little bit more because, of course, we still need the ratio and root tests. But these are usually pretty quick. So we're going to be really doing this. We're going to take the absolute value and see if that tells us something about our original series. Right, so for this example here, this is kind of a tricky one, but let's see. So, you can try to plug in numbers and see what happens, but it's really hard to monitor because we have cosine of integers, and we don't really know anything about cosine of integers. We know cosine of multiples of pi and stuff like that because it's in radians, of course. But when you have cosine of like 3 or 2, it's hard to tell really what's happening. And in fact, cosine alternates in sine just like sine does. It goes in between -1 and 1. So it's really hard to tell if this is convergent. And by the way, this example is asking us to test for convergence. But what we can do is we can, instead of looking at this, let's instead look at the series over the absolute value of these terms. And by the way, if you take the absolute value of this, n squared is always positive. So its absolute value is just itself. The absolute value of the numerator, that's a different story though. Because of course, since cosine alternates between sine, absolute value of cosine will obviously not be itself. Sometimes it is, sometimes it isn't. So this actually makes sense for the numerator, but the denominator, the absolute value of n squared is just n squared. Now what can we say about this? Well, if we take a look at the inside, since the absolute value of cosine of n is in between 1 and 0. In fact, you know what? It's never going to be equal to 1 and it's never going to be equal to 0. And the reason I know that is because cosine is 0 when n is pi over 2 or 3 pi over 2. and it's 1 when n is 0 or pi or 2 pi and so on. And integers can never be equal to those multiples of pi over 2. So as it turns out, this is a strict inequality. And we can actually say by the comparison test that this is less than this right here, replacing the numerator with 1. And these are for sure positive terms. So again, for comparison tests, all we need is that they're all positive terms. And these are always positive, just like we just discussed. And this inequality holds for all values of n. So by comparison test, we can say, since this converges, and this is, well, less than this thing that converges to some number, this implies that this actually converges by comparison. That converges by comparison. And what does that mean about our original series? It means that this has to be absolutely convergent because the series over the absolute value terms converges. So this implies that this original series from n equals 1 to infinity of cosine of n over n squared is absolutely convergent, which implies convergence. Awesome. But it's pretty tricky because, to be quite honest, this is basically the only way of doing this. Well, kind of. So now we enter the ratio test. And the ratio test is a very, 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 very strong and broad test. What the ratio test really does, there's no way I'm going to have time to prove it here, but what it actually does is it tries to relate a series to a ratio, not ratio, but to a geometric series. I said ratio because geometric series have this ratio. If you recall, when we saw a geometric series, we saw that it would converge if the ratio was less than 1, diverge if the ratio was bigger than or equal to 1, actually. And as it turns out, in general, when the ratio is equal to 1, it's kind of not the case that it'll actually be divergent, but we'll actually see that when we run through this. So what we need is the following. We need to basically study the limit as n goes to infinity of, well, basically the next term in the sequence over the term we're at. So really a sub n plus 1 over a sub n. If that limit exists, and it's L, then the following is true. Either it's less than 1, greater than 1, or equal to 1. And that's it. So if it's infinity, for instance, well, then that's bigger than 1, so it diverges. Okay. Now, again, if it's less than 1, it's absolutely convergent. And you know what? I kind of made a small mistake here. These should be an absolute value. So we want to take the absolute value of the quotient of these terms. This will give us absolute convergence, which implies convergence. And in fact, the ratio test says this. It doesn't say it without absolute value. So that was my mistake not writing those. And if it's limit's bigger than 1, then it's divergent. And if it's equal to 1, then there's no conclusion. In other words, the ratio test is actually inconclusive. Now, for this example, we'll take a look at, let's see, it's a sum from n equals 1 to infinity of 1 over n factorial. We actually saw this in the past when we looked at comparison tests. And just to recall what factorial does, is it multiplies 1 to 2 to 3 all the way up to that number n. So in this case, when you plug in 1, you get 1 over 1 factorial, which is just 1. 2 factorial is 2, so it's 1 over 2. 3 factorial is 3 times 2 times 1, which is 6, so it's 1 over 6. 4 factorial then would be 24, and then 5 factorial is 120, and so on. Okay, good. So we have this series, and if you go back to that section, we actually found out by comparison that this actually converges. And now what we're going to do is we're going to try to use, the ratio test. So let's see. We're going to consider the fact that a sub n in this case is 1 over n factorial. And what we want to find is we want to find the limit as n goes to infinity of the absolute value of a sub n, so it's 1 over n factorial, over, the numerator is a sub n plus 1. So let me just write it like this, kind of formally. I was trying to skip a little bit, but it's best if we just kind of show our work and go step by step. So we have a sub n plus 1 over a a sub n plus 1 in this case will be 1 over n plus 1 factorial. That's a limit as n goes to infinity. Hopefully we have a little bit of space here. So it's 1 over n plus 1 factorial, just like that. Over the denominator, a sub n, is just 1 over n factorial. So, if we multiply the top fraction by the reciprocal of the bottom fraction, we get 1 over n factorial, well, 1 over n plus 1 factorial, times the reciprocal of the bottom, which is n factorial over 1, like that. And we're still in the limit, and we're also still in absolute values. So what's the great news here? Well, the great news is that this is n factorial over n plus 1 factorial. An absolute value, and then limit. A lot of decorations. Now, n plus 1 factorial, if you expand it out, is n plus 1 times n minus 1 all the way to 321. In other words, we can write the denominator as n plus 1 times n factorial. Great. Why is that so great? Of course, you can kind of see it. It's because the n factorials cancel. We're left with 1 in the numerator. And then we can clearly tell as n goes to infinity, 1 over n plus 1 goes to 0. So this actually goes to 0. So since the limit in this case is 0, let me just say L equals 0 implies convergence, well, specifically absolute convergence, by ratio test. Awesome. Really what we care about is if it converges, but ratio test is so strong it gives us absolute convergence actually. And what's kind of funny is that this will kind of tell you that any series that is conditionally convergent, if you apply the ratio test, it's going to be inconclusive because you only have these choices really if you're not inconclusive. And we know if it's conditionally convergent, it can't be absolute convergent. And since it's convergent, it can't be divergent. So the ratio test would have to be inconclusive there, which is interesting. But with that being said, we'll take a look at a few more examples, and then we'll finally take a look at the root test. All right, so now testing for convergence or divergence with these two examples here, I want to try to use the ratio test, of course. Now, what you may expect me to do is, well, this is a sub n. So you may expect me to write the absolute value of a sub n plus 1. So replace n with n plus 1 everywhere you see an n, write n plus 1 instead, and then divide this by the original a sub n with just n's instead of n plus 1's. And then multiply the top by the reciprocal of the bottom, and yeah, I kind of just did it. But there's something to learn from this. Since we're taking the absolute value, do we even need the negative 1 to the powers? We don't. In fact, if you take a look at this, well, what ends up happening actually is that we get this. So I'm going to write the top times the reciprocal of the bottom. And we'll have some cancellation of the powers for, well, for a few things, but let's just kind of take it step by step, I guess. So reciprocal of the bottom will now be 3n on top and negative 1 to the n, n to the third on the bottom. Good. Now again, with the powers of negative 1, they cancel like this so that there's only negative 1 to the 1. But it doesn't really matter because since we're taking the absolute value anyways, the negative is basically disregarded regardless. And in fact, here also we have cancellation of the 3n's. So this is, notice a very similar thing happens. If you cancel 3n with 3n, 3 to the n with 3 to the n, you end up with 3 on the bottom. Basically, 3 to the n plus 1 is 3 times 3 to the n. So when you cancel, you only have 3 left over. So I'm just writing it like this, so it's 3 to the 1. So all we have left really is the absolute value of negative n plus 1 to the third over n to the third. And that's just equal to the absolute value of n plus 1 over n all to the third. So what I'm doing here, of course, I'm saying what I said earlier. You can really just ignore the negative part, the alternating part, which makes sense because what does the ratio test do? The ratio test checks for absolute convergence. So if you're looking at an alternating series, just take the absolute value of the terms, and in other words, ignore the alternation part, the alteration part of the signs. and you get this. And as n goes to infinity, this goes to, well, I guess it goes to 1, doesn't it? I'm missing a 3 though. There we go. Otherwise, it would go to 1 and we'd be in trouble. So actually, as n goes to infinity here, you ignore, by domination, you ignore this plus 1. You get n over 3n, which is 1 over 3. And this actually approaches 1 over 3 to the third, which is 1 over 27 in the limit, which is less than 1. So this arrow denotes the limit as n approaches infinity. So notice in this notation here, I'm not writing the limit as n goes to infinity each time. I'm just looking at the expression we want to take the limit of as n goes to infinity. And then once I've simplified enough, I'll write an arrow and then take n to infinity. So in reality, I should be writing as n approaches infinity under this arrow. But that's kind of implied, basically. So since it's less than 1, then by the ratio test, this is absolutely convergent. So let me write absolutely convergent by ratio test. Perfect. Now, this one is a little different. It's actually kind of the same idea. So the ratio test will always have the same idea in mind. But we're going to try to get used to this idea that we want to, instead of writing a fraction as the ratio test kind of leads us to believe we need to set up, we understand that it's always going to be, if we have our a sub n term being a fraction anyways, then it's always going to be that with n plus 1s times the reciprocal of this. So really what I want to set up is the absolute value of this with n plus 1s instead of n's, like that, times the reciprocal of it with just n's. So n factorial over n to the n. Now there are a few things we've learned from factorials that we saw in one of the previous examples. Notice n plus 1 factorial is just n plus 1 times n factorial. So these actually cancel out straight up. Okay. What else can we do? Oh, I guess so we can cancel one of these. So n plus 1 to the 1 cancels with one of the n plus 1s up here completely, and we're just left with n plus 1 to the n. And this is nice because notice these all have the power n. So in reality, this is the same as the absolute value of n plus 1 over n to the n. And kind of like here, even though I didn't say it, since n is positive, we actually don't care about the absolute values at this moment. So really we can just drop the absolute values. Because since n is positive and everything's positive here, these are positive numbers anyways. And absolute value of positive number is still positive. Now this, if it doesn't look familiar, let me try to make it look a little more familiar. If you split it up, n over n is 1, plus 1 over n, all to the n. Maybe it still doesn't look familiar, but it should. This actually is e in the limit. So as n goes to infinity, this expression will get closer and closer to e to the 1. And in fact, in general, whatever this numerator here of the 1 over n part is, will be the power of e. So if it was 1 plus 2 over n to the n, that would approach e squared as it turns out. And this is actually greater than 1, isn't it? So that implies this actually diverges. So this is divergent by ratio test. Perfect. Now, to be quite honest, this is kind of the most interesting it gets as far as ratio test goes. And you can try other examples on your own, but you'll see that the techniques I've showed throughout these examples, and the previous one, I guess, are really going to be used throughout for ratio test. Now we're going to take a look at the root test. Right, so finally now the root test says that if the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to L, then we have very similar consequences as we did with the ratio test. If L is less than 1, the series over a sub n is absolutely convergent. If L is greater than 1, the series is divergent. And if L is equal to 1, the ratio test or the root test would be inconclusive, just like the ratio test would be inconclusive. And I'm really only going to do one example here. And I strongly believe we actually only need one example because the root test is a very specific type of test that is basically designed for problems like this. What I mean by that is that if it's a sum whose general term is all to the nth power, then you apply the root test. because it gets rid of that nth power. So now, by setting up the root test, what we want to do is look at the nth root of the absolute value of this. And I'm allowed to do what I just did here, because of course, when you take the absolute value of a power, it just affects the base only, and then you take the power of that. Basically because absolute values are multiplicative. So now notice these cancel, so that's kind of the main reason why we want to use a root test for this case. And like I said, the root test is basically specifically designed for these kinds of problems. Now we're just taking a look at this expression only, and again, like we saw before, since n is positive and there's no negative in sight, this expression will actually always be positive as it turns out. Very good. And in the limit, well, if you do domination, use the idea of domination, 1 is negligible, 2n over 3n, the n's cancel, so you get 2 over 3, which is less than 1, so this is absolutely convergent by the root test. Perfect. So you'll get very similar results as you would for ratio test because it's almost the same. In fact, I believe the proof for the root test is based on the ratio test. It's just a specific application of that for series that have general terms that are to the nth power. So I didn't even write out, in fact, I haven't really been writing out terms for a series in a while. But you can always do that just to get an idea of what the series is doing. But if it has a particular type of look to it, like for instance all to the nth power, then you consider specific types of tests, like in this case, the root test. So now we're going to move on to chapter 11.7 in the next video. And 11.7 is a compilation of everything we've seen up to 11.6. Really, it is strategies for testing for convergence. So we're going to take a look at that in the next video. Thanks for watching. I really hope you enjoyed this video. See you then.